I am going to call this problem distributed joint panes. So the diagnosis of a condition called distributed joint pains is dependent on a test called Jpmf. The test accuracy is studied and the data is given below. Of course, we want to see how accurate a particular test is. You can change the condition to anything. You can convert it to code if you want to understand this problem. And that is what I have. And I'll call the condition to be the random variable x, the test result to be the random variable y. We have to give labels to the condition because we can't directly use positive and negative when we do calculations. So I'm going to call positive as 1 and negative as 0. Saying positive 1, negative 0. So first, we want to find the marginal distribution for the Jpmf outcomes. Jpmf is the test that I'm using. And I would like to find the marginal distribution. How do we find the marginal distribution? We need to get the totals first. So 120 plus 80. 200, 300 plus 12, 312, 512, over here, 132, 380. If you add the two, you should get 512 as well. We want to find the marginal distribution for the test outcomes. Well, what is the sample space of y? I move from labels over to numbers. So what is the sample space? 0 and 1. Next, we want to find the probability of y to get the distribution. So what is the probability of y? Well, for 1, it is 200 over 512. For 0, simply 312 divided by 200 over 512. The outcomes for x, 0, 1, 0 being negative, 1 positive, and probability of x would simply be 132 divided by 512 and 380 divided by 512. Yes? Did I mess that up? Oh yeah, just looking at the wrong thing. 80, 132. Now that we have the marginal distributions, we can go ahead and find the expectation. That is straightforward. Expectation of x, we simply have to multiply the probability with the outcome. So 0 times 380 over 512 plus 1 times 132 over 512. Expectation of x, expectation of y, 0 times 312 over 512 plus 1 times 200 over 512. Which is 200 divided by 512. Here is a question. Does it matter if I called it as 0, 1, 1, 2, or 2, 3? No. It does?
Well, the expectation would be different. The expectation would be different.
Okay, so could I have a different label instead of 0 and 1? Could I have it as 1 and 2?
Well, what I'm saying is that at the end, the expectation would be different because they're multiplying by.
The expectation will be different, I agree, but would the interpretation change in any way? No, it's not going to. As long as it's a unit interval apart, it's not going to. 1 unit apart. Otherwise, we're introducing bias. What do I mean by that? What is that value? About 20%. How much? And for the other one, 2 over 5.
3906.
Right. So the interpretation would simply be rounding it to the nearest integer, right? So we would round it to 0 in both cases. If someone asked you, is this condition quite prevalent on average, what would you think?
I guess, like, depends on that's never subjective.
kind of subjective. On average, is it very prevalent?
Quarter of the time, I guess.
Quarter of the time. How does the test do in terms of positivity, identifying positivity? About on average 0.3906. But these aren't good measures to assess the accuracy of the test. We need probabilities. Do I have the joint distribution for X and Y? What is the joint PMF? Part C, or no, part D. Find the joint PMF. Joint probability mass function. Now you sort of see where I got the test name Jpmf from. How do I find the joint PMF? So what I have is a contingency table. All I have to do is divide each value in the contingency table by the total. So I would have 120 divided by 512. Okay. 80 over 512, 120 over 512, 300 over just stick to what I have. So 1010, 120 over 512, 80 over 512, 12 over 512, 300 over 512. So all I did is I took each value divided by 512, because if I add all joint probabilities in a joint probability mass function, it has to sum to 1. And here it will sum to 1, there it wouldn't. So this is a valid joint PMF. Now, are the random variables independent? We can say that two random variables which have PMFs and a joint PMF to be independent if probability of X is equal to little x, Y equals Y, is equal to probability of X is equal to X times probability of Y equals Y for all X comma Y. That has to be true for every single X and Y. One of them violates the condition, we're done. So we just have to pick one. Go ahead, pick one. 1, 1. The joint probability of 1, 1 is 120 over 512. What is the probability of X is equal to 1? 132 over 512. Probability of Y equals 1. 200 over 512. If you multiply those two, would that equal to 120 over 512? No. So there is dependence. So in this case, we can't say things are independent. Which should be the case in a practical sense, right? If your test does not depend on the type, the presence of the condition, or if the condition doesn't depend on the test itself, then what is the point of having a test? The test has to have some relationship with the presence of the condition. So they have to be dependent. Are we clear? Yes.
So we know they're dependent because those things aren't equal to each other?
Yes.
Okay.
Okay. F. Oh yeah. Forgot my alphabet. Right. And before we start, how many conditional PMFs would we end up having? 4. Why 4, Chris? Because there are 2 of each. In other words, I can find the conditional PMF of x given y equals 0, and x is going to take 2 different values, 0 and 1. And what is that? Conditional PMF. So conditioned on a negative for y, so that would be my total. The probability of a 0 is 300 divided by 312. Conditioned on y equals 0, we will have 12 divided by 312. Yes? I want you. Huh? No, 312. Conditioning on this case. Of course, you could use the multiplication rule to come up with this probability. Joint probability divided by the marginal probability. But either way to remember or understand this is when you condition, you're not looking at the total sample size, rather you're conditioning on the total corresponding to that particular level. I want you to find the other 3 conditional PMFs. So we want to find the conditional PMFs. The second one would be x given y equals 1, 2 possibilities, 0 and 1. So probability of x given y equals 1, condition on y equals 1, I would have 120 divided by 200. Of course, you can simplify that. 80 divided by 200. Yes. The next one would be y.
If you flip them.
Oh,
For the
I don't know why I keep
Y
doing this. AC and 120.
It's really flipping every time. When I go 0, 1.
I should have just kept it as 0, 1. Y given x is equal to 1. So when x is equal to 1, I'm conditioning on this. So the total would be 132. So 12 divided by 132. 120 divided by 132. That would be the probability of y given x is equal to 1. The next case, y given x is equal to 0. X is 0. I have two possibilities for y, 0 and 1. Conditioned on x is equal to 0. Probability that y would be 0 is 300 over 380. Conditioned on x is equal to 0, y being 1 is 80 divided by 380. So we end up having 4 different conditional PMFs. The moment conditional probabilities come into play, things do get pretty complicated. Which is why when we do Bayesian analysis, we have to use a lot of simulations and stuff, because you have to evaluate a lot of possibilities. Here is the question. How do I phrase this? Those random variables. Yes, no, maybe. So my question is, are these random variables themselves?
Whatever conditions of various events are effects.
Yes or no? Are they? If you say yes, you've got to tell me why. If you say no, you've got to tell me why.
They're not variables because you said that a few weeks ago.
Come again?
They're not random variables because you said that a few weeks ago.
They're not random variables if I condition it on a single value, right? In other words,
I believe that's what you said a few weeks ago.
like x is equal, okay, if I said x is equal to 0, given y equals 0, that's not random, right? That by itself. Now here I have y equals 0, conditioned on y equals 0. Does x have one single value? It could have 0 or 1. Do they happen with certainty on one or the other? They have a probability distribution. If each of those have a probability distribution, then they're all random variables themselves. So if those are random variables, I can find expectations for each of those, correct? Yes? Those expectations are what we call conditional expectations. How many conditional expectations would I have? Four. So The first one, other than the first one, you could do the rest. Expectation of x given y equals 0. Yes. And that would simply be 12 over 312 because you're multiplying the outcome 0 by the probability 300 over 312 plus 1 times 12 over 312. So we get 12 divided by 312. Quickly, you could find the rest. So go ahead and find the expectation for the other 3 random variables. Straightforward. So expectation of x given y equals 1. I'd end up guessing 120 over, oh, looking at the wrong thing. 120 divided by 200. Expectation of y given x is equal to 1 would be equal to 120 over 130. Likewise, expectation of y given x is equal to 0 is 80 over 380. Good. So all of these random variables, if I simply condition on one single value of x and one single value of y, it's not a random variable. But if we have multiple possibilities conditioned on one single value of y, then we have a conditional Pmf. Can I erase this part? So we have the expectations. Those are called conditional expectations. Is this a good test? The Jpmf. Is it a good test in detecting the distributed joint pains condition? Shane?
It looks like the test produces a lot of false positives, but if the test, it doesn't produce a lot of false negatives, or like a lot of false, it does produce a lot of false positives, but there's not a lot of people who sneak through who have it and test.
So you are right. So the false positive is pretty low, right? If the condition is not there, but if the test concludes that it's positive, that false positive is pretty low. Likewise, the false negative, if you're positive and the test concludes as negative, that is also low. But is it a good test overall? Yes, because it doesn't make a lot of error compared to the totals. Ideally, one would want 0 here, 0 there. That's ideal, but not going to happen in practice. So overall, good test, I would say. We could also look at the average. In this case, the averages are simple probabilities. So we could use the conditional expectations to come or make a similar argument. This is all good. Here is another question. If I define part G H W is expectation of x is equal to W given y equals 0. Let's frame it properly. X is equal to W, Y equals 0. Give me 1 second. So if I define W equals expectation of X given Y equals W, but W could be 0, 1, is W a random variable? Based on what I wrote, we cannot come up with a direct PMF for W, yes? Because we have to normalize that PMF in order to, normalize the distribution to get a PMF. And the only way that's going to happen is if I look at all 4 possible outcomes. In other words, X is equal to 0, given Y equals 0, X is equal to 1, given Y equals 1. Do the same thing time and time again. So based on the way I wrote this, it may seem that W is not a random variable, but X, I'm going to assume, is going to take all possible values, both 0 and 1. I'm not going to constrain X to be one single value. X is random in and of itself. So W, in that case, will be a random variable. Does that make sense? So X can take both 0 and 1. I can vary W 0 and 1. So expectation would also be a random variable. But we will just have 4 possibilities. Good. Now, what are the 4 possibilities? I got to say 0 given Y equals 0 is 1, 0 given Y equals 1, 1 given Y equals 0, 1 given Y equals 1. 4 possibilities. Add them all together, it is going to give us 1. It will have a PMF. But that's not where I'm going with this. Now, what would happen if I took the expectation of this expectation? That's what I'd like to know. Expectation of W. That would simply equal expectation of X given Y equals W. Yes? When I evaluate this expectation, it would be with respect to the PMF of Y. Do you agree? Because there are 2 possible values for Y. So if I'm going to evaluate this expectation, I'm going to fix X to be a random variable. I'm going to evaluate when Y is equal to 0 and when Y equals 1. So we can use law of total probability to come up with this expression. When we do that, this would reduce to expectation of just X. Oh, put 2X. I mean, I can write it that way also, but all I meant to say was that will equal to expectations of X. So expectation of expectation of x given y equals w would simply be equal to expectation of x. And that's condition where we say expectation x given y equals expectation of x. It's called the law of total expectation, LTE, or law of iterated expectation. LTE, lie, one and the same. So expectation of x given y would simply be equal to the expectation of x if I took expectation one more time. Now let's use our example to see if that works out. This would mean I've got to condition it on two values, correct? For y. What are the two values? The values for y in this case are 0 and 1. So since I'm finding the expectation, I've got to find the probability y equals 0. That's a random variable. Multiplied by the expectation of x given y 0. Outcome, probability, outcome. Because I'm treating that as a random variable. W equals lowercase w. The value of w now is 0. Yes? Plus probability of y equals 1 multiplied by expectation of y equals 1. X given y equals 1. Probability of y equals 0 and probability of y equals 1. I just jumped ahead. So since I'm treating the expectation as a random variable, that is w. And w has two possibilities, and those two possibilities are dependent on y, which is y equals 0, y equals 1. So when I condition on y equals 0, the corresponding probability will be probability of y equals 0. The outcome would be the expectation. Plus the probability of y equals 1, the outcome would be the expectation of x given y equals 1. Now, what is the probability of y equals 0? From here, that would be 312 over 512 times the expectation of would be 12 given 312. Yes? Plus probability of y equals 1 would be 200 over 512 multiplied by expectation of x given y equals 1, 120 divided by 200. So the random variable w has two outcomes, w equals 0, w equals 1. When W is 0, the probability of that happening is probability that Y equals 0. When W equals 1, the probability of that happening is probability Y equals 1. So if I use those two expectations, this number and that number would go away, that and that would go away. 12 over 512 plus 120 over 512, 132 over 512, that basically equal to expectation of x. That's the expectation of x. Now, this process is going to get painful if we have more outcomes. Suppose we had 0, 1, 2, 3, 4 for y. Then y equals 0, we have to find the first expectation multiplied by the probability of y equals 0. The second expectation multiplied by the probability of y equals 1. Another expectation, 2 and 3. Repeat the process. When we get to joint PDFs with continuous random variables, this is easier to show via integration. So I'll do this again when we do it with continuous random variables. Good? So the key to remember is expectation of expectation. X given y will be equal to expectation of x. Now, where does this go back to? This goes back to unit 1. Can you tell me what topic it would be? This should be similar to something from unit 1. We are summing over all possibilities and we are conditioning. Conditioning, summing over all possibilities. What? Conditioning, summing over. Hint. Close. Hint. The hint is total. Law of total probability. The denominator in base rule is law of total probability. We condition and then multiply the probability and sum it over all possible values. That's exactly what I'm doing. Each outcome, summing it over all possible values where each outcome is an expectation. So, which is why we call it the law of total expectation.